Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with another geometry video for you all. This lesson topic is all about rectangles, triangles, and composite figures. So we're going to be looking at different properties of rectangles and triangles, as well as identifying what exactly composite figures are and the different correlations they have with polygons that we already existingly know. So before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. The whole theme and purpose of today's lesson is to discover what are the area and perimeter formulas for rectangles, as well as some other extended relationships with them and amongst each other, so some similarities between rectangles and triangles. And we're also going to identify what exactly composite figures are if you don't already know what they are. And we're going to also identify different compatibility relationships and different polygon relationships that they have. So without further ado, let's get right into it. So we're going to first look at properties of perimeter before we actually get into jump into a further topic in today's lesson. So perimeter of figures. Perimeter is the distance around a plane. If you don't already know what perimeter is in basic terms, it's basically the distance around any 2D figure or any polygon in general. But I'm saying here the distance around a plane just because a plane refers to a two-dimensional outlook out of a three-dimensional overview. So we're going to look at a perimeter, and it's the distance around a plane. So if you haven't already seen previous figures such as triangles and rectangles before, all you're going to do is add the sum of the side lengths. So perimeter of polygons specifically, which also exist on planes, is the sum of all sides. So it's the sum of all sides that are given in length on any type of polygon, and that is inclusive of the shapes that we're going to look into today. And when finding the perimeter of any figure, make sure all side lengths are of the same unit of measure. If you're going to be adding these side lengths up together in order to get your actual perimeter of that specific polygon, you need to make sure that all side lengths are in the same unit of measure. Distance and length is always going to be expressed in some sort of unit form, and if it's not necessarily given a specific unit form in the imperial system or the metric system or any other system that you can calculate through, it's going to be represented by units, and it's units cubed, units squared. Units squared is representative of area, units is representative of perimeter, and units cubed is representative of volume, but we'll get into volume later. So this is what it is, and to find the perimeter of a shape, we need to add the length of all sides. If we're given this square here, say for example, we're going to be adding all sides of that square, which is 4 plus 4 plus 4 plus 4. So you're just going to add all sides. 4 plus 4 plus 4 plus 4 equals 4 times 4, which is 16. So that's 16 centimeters. And that's going to be 16 centimeters alone because that's our unit of measure. It's not going to be squared or cubed or anything just because it's a singular measure, and it's not going to be of cubic or square measure. And also there's a neat shortcut for squares when you're trying to calculate the perimeter. All you need to do is multiply a side length by 4. So you're going to take the side length, since we know that the sides of a square are always going to be equivalent and congruent to each other. We can merely multiply the one side length by 4 to account for the rest of the side lengths. So that would be 4 times s. If you just wanted to, I'm just going to throw that out there just in case if you didn't already know. It's just a bit of a shortcut, but it's nothing too far from the area of a rectangle. So let's look at perimeter of triangles. And before I move on, I also wanted to add area of figures as well. So the area is basically the square units contained within a figure. So that means if you would take some sort of dimension of any figure, including a rectangle, a square, which is a type of rectangle, or even triangles, and you're going to be multiplying some sort of dimension in order to get the amount of space that's within the actual figure. So you're going to calculate the amount of space that's within that polygon by multiplying the certain dimensions together under a certain accounted formula. So that's area as well. So let's look at perimeter of triangles. So we're going to see how we calculate the perimeter of triangles. How I organize this lesson up is we're going to be focusing on the area and perimeter of triangles. Then we're going to be moving on to rectangles and focusing on the area and perimeter and some shortcuts and other specific relationships. And finally, we're going to get to composite figures, and I'm going to do practice problems on all of these topics that we're going to refer to today. So let's look at calculating the perimeter of triangles. The length and width of a triangle are also known / referred to as the base and height. So if you look at a triangle has 3 sides on it, and it is referred to as a length and width. So you do always have a length and width of any figure that's given, but the length and width of a triangle are known as the base and height. So you're always referring to a triangle. The 2 important dimensions that you need in perimeter and area is just the base and the height. And the formula of the perimeter of a triangle remains consistent for all triangles, no matter what type of triangle it is. Unlike parallelograms or specific triangles actually have a consistent formula for all types of triangles, which include all of the angle classifications and the side classification. Triangles like scalene, obtuse, you might even have isosceles, things like that. Yeah, and the equation is the sum of the base, height, and the third leg. So if you were given a triangle here, I'll draw this out. Basically, what I'm doing is I'm taking a shortcut of the perimeter equation. So the perimeter of a triangle is merely just the sum of all of its 3 sides. So if you're given 3 centimeters here, 4 centimeters here, and 5 centimeters here, all you would do is you try and keep this consistent. You try and see if all units of measure are consistent, and then what you would do is you would add the base, the height, and the third leg, and that's only if you're referring to a right triangle. So this is a shortcut for a right triangle, but in any triangle, it would just be the sum of all sides, just as the perimeter. So any triangle, I'll write it here, any triangle equals sum of all sides. And the reason why this little shortcut here, the base, height, and the third leg, applies to a right triangle is merely the fact that the base is one leg of a triangle. The base will always be a leg of a triangle, but the height won't always be a leg of any triangle in specific. It will only be the height the height will only be the leg of a right triangle, meaning the base and the height will always be side lengths of a right triangle. Therefore, the third leg will be the third leg of that triangle, of the right triangle, and you can merely add the 3 side lengths. So I'm just saying you're adding the 3 side lengths of that right triangle, which applies for any type of triangle. So let's move on. Let's look at the area of a triangle. So let's derive the equation of what exactly the area of a triangle is and where it is actually, its origins, where it actually comes from in geometry. So the base of the triangle can be any side due to the fact that a triangle can be rotated on its center, but the height will always stay consistent. So notice how I said the base and the height. Well, in any triangle, in any case, it doesn't necessarily have to be a right triangle. Every triangle has a given height, and I will explain that in my later videos. Every triangle has a given altitude and height, and that's always going to stay consistent, meaning the height of a triangle will always remain the same. However, the base of the triangle is always relative, meaning the side that is going to be directly on the bottom of that very figure, meaning the side that is closest to the bottom. It can be identified, given it might not necessarily be on the bottom, but if it's not identified in any problem, you're going to assume that the side closest to the bottom would be the side that is the base. So it's always going to be a matter of fact that you're going to multiply the base times height, and it should always stay consistent. And one cool fact about the base is that it can have a different location, but it will always be the same side length, is what I'm trying to say. So the height will always be perpendicular to the base, and that's how you identify the base. Meaning perpendicular, meaning it forms the right angle at its intersection of the base. And the formula for the area of a triangle is area equals base times height divided by 2, and this originates from the rectangle, the number of square units given. So if you're given a right triangle, so the only time that this equation will work without actually being given a height or altitude in a triangle is when you're given a right triangle. So today we're only going to be focusing on using this equation for right triangles, but I will definitely go over that in my very next lesson, which will be more about rectangles and triangles and composite figures. So that's just a bit of like extended problems, just as I had done with dilation. So let's just focus on the right triangle here. And then from one of my practice problems, I'll give you a bit of a glimpse in what the next lesson will be like for geometry. So I'm drawing out a right triangle here. And we're going to use this equation, base times height divided by 2. So if we're given all you need in this case, sorry, let me just erase that real quick. So all you need in this scenario is technically the base and the height, because 2 is a constant and we already know what that value is equivalent to. So if we're looking at the base and height, all we need is the base down here. So I'm going to put that as 8, and we're going to make this height here 4. So we're going to plug this into our equation, these values, and I'm just going to indicate here that it's the right triangle with the right angle. So we're going to do this, calculate this. So it's going to be 4 times 8 over 2 equals 32 over 2, which equals 16. And that's going to be unit squared, since I did not specify a specific unit. And since it's area, you're going to be calculating in the number of square units. So that's where I'm deriving that unit form from. Now, I wanted to really emphasize on the fact that I said it originates from the rectangle. Well, it's only specific to a right triangle. Today's focus is more of right triangle and deriving the equation with the right triangle. The reason that this equation is derived from the right triangle is because, it's derived from a rectangle through the right triangle is because if you look at a right triangle here, just like this, and if you were to double this figure, meaning if you put this a congruent triangle, the same exact triangle, and if you were to take it and you're trying to put the longest side, the hypotenuse, and you're trying to match that up, you'd be forming two triangles that are of the same length connected together. And when you actually connect them, you're forming a rectangle with a height, with a length of 4 and a width of 8. So 4 times 8 would be the area of this entire square here, or rectangle, depending on what the side length measures are. But this is what rectangle in this case. So you'd be actually calculating the area of the rectangle, which is 32. However, since this right triangle is only worth half of this entire rectangle, you're just going to divide it by 2 to get 16. So 32 divided by 2 is 16 units squared. Now let's move on to the perimeter of rectangles. So let's calculate the perimeter. The lengths of a rectangle are the two sides that are parallel and opposite from each other, as well as perpendicular from the width. So the two main dimensions given in a rectangle are the lengths and the widths, and those are most important in calculating both the perimeter and the area of a rectangle. That's the only thing that we worry about in this case. So if you look at what I stated here, the length and width are not necessarily going to be exact sides. They just have to be relative with each other. So if you're given a rectangle, I'll draw out a rectangle here real quick. So if I draw out a rectangle right here, just to further prove my point while I explain it. So if you look here, the two sides that are opposite from each other, they can be either lengths or width. So these two sides, as you can see, they're opposite from each other, and by the definition of a rectangle, they're going to be congruent. And these two sides can be either the length or width. But if these two sides, you can make it up, you can choose length or width. So if you identify this as length, just by chance, just if you wanted to, if you felt like it, then these two sides would be the widths. So this would be width, length, and that can always be flopped, but the relation has to be the same, meaning opposite sides must be of the same type, meaning opposite sides will always be lengths, and the other perpendicular opposite sides will be widths. And the reason I said perpendicular is because the length of any side of any rectangle is always going to be perpendicular to both widths. So it's going to form a 90-degree angle when intersecting both of its widths. And the formula for the perimeter of a rectangle is 2 times the length plus 2 times the width. So L, I'll write this here, L equals L equals length. I apologize. L equals length. And W equals width. So you're going to be doing 2W plus 2L. And all that is you're taking these sides, and in essence, it's just adding all the sides of a rectangle. You're just adding L plus W plus L plus W, or one side plus the second side plus third side plus fourth side. But this is a bit of a shortcut. So you're taking W, you're taking 2 of W, so that's taking this side. You've accounted for this side and this side by doing 2W, and then you've also counted for L and L, these two sides here, by counting for 2L, and that will equal your perimeter. So that'll equal perimeter. Now let's move on to the area of a rectangle. So we're going to derive the equation for the area of a rectangle. The area of a rectangle, which includes a square being a type of a rectangle, meaning it's not just your standard rectangle. It also includes a square. It's length times width, and I just want to clarify: a square is a type of rectangle, so this will always apply for a square as well. So the area of a rectangle is length times width. So given your length measure and your width measure, it's just going to be length times width. And this is true because you can prove it by looking at a coordinate grid. So now that we've actually identified what the equation is, we're going to try and look and seek for the origin. So that comes from the coordinate grid. I'm just going to write this out here. If you don't understand this in keyboard language, I'm just going to write this out here. Length times width. So it's the length times the width. So I'm going to show you a little example on the coordinate graph. This is a coordinate grid here. It has gridded points. So if I were to draw out a rectangle here, and I'm going to give it so the only two measurements that we need is one length and one width. So I'm going to label this as 8. I'm going to make that my length, and this as 4, and I'm going to make this as my width. Same as the previous one with the right triangle. I'm going to use the same dimensions and keep it consistent. So we have 8 and 4 here. If you plug this into the equation, we get that 8 times 4 equals 32 units squared, because you're calculating area. So that's going to be units squared. And after we look at this triangle, this rectangle, we're going to try and prove this by putting it on a coordinate grid. So I'm going to try and label this out on a coordinate grid. So we'll count 8 units up. Let's count 8 units up here. And we're going to try and graph each point on this grid. So let's just clear that up. So we'll count 8 units up. So 1, 2, 3, 4, 5, 6, 7, 8. So that's right here. That's one point. This is our second point. And all I'm doing is I'm just transferring this rectangle here onto this coordinate grid with its units of measure. That's the length. And then 1, 2, 3, 4, 4 over. And now I just want to make this specific. These two measurements are supposed to be flipped. I apologize. So this is supposed to be 4 and 8. Yep, 4 and 8. And I made the same mistake in the previous one, so please ignore that. It does not matter, though. Even if you mix them up, it's still going to apply for the equation properly. It's just that it's not drawn to scale. So I apologize that in advance if you had caught that previously. Yeah, and I'm just going to clarify that here. So this is our length of 8 right here. And then this is going to be our width of 4. I'm going to draw this rectangle right here. Now, we see that there's 8 by 4, and you're going to multiply 8 by 4 to get 32 with our equation. So how do we prove that? We're going to look at 8 and 4. We're going to multiply that, and we see that it's 32. But another way that we can prove this is by counting the amount of squares inside this grid. So if we count this out, and I mean literally count this out, if you count all of these squares out inside and on the inside, it's 8 by 4, which will be 32. So if you count all these squares, these units squared, square units, you're going to get 32, and that's how we actually prove this, by literally facing it out on a coordinate grid and counting the amount of spaces. And finally, let's move on to the area and perimeter of composite figures. So let's look at the perimeter and area properties that they have, since they are relative types of figures. So composite figures, if you don't already know, by its own definition, is a figure made up of 2 or more figures. So basically, a composite figure is when you take one figure and you mesh it with one or more figures. So it's just a bunch of figures connected together at their side lengths. And the perimeter of composite figures is just basically the sum of all its sides, sum of all its exterior sides that are not on the inside, but sides that are on the outside of the figure, of the plane. And the area sum postulate, which is basically proving the area of a composite figure, is that stating that if a figure is made up of non-overlapping figures, which is a composite figure, then the area of the figure is the sum of the area of its parts. So in order to calculate the area of a composite figure, you're just going to split up that figure into polygons that you actually know the formula for, the area formula for, and then you're going to calculate their separate areas, add them together to get the total area of a composite figure. So this is an example of a simple composite figure here. You can split this figure up like down here, right here, and make a partition, and you get 2 different rectangles. So I'm going to label this rectangle 1 and rectangle 2. And all you need to do is calculate the length and width of these rectangles. So you're going to try and find the length here. Use your properties, subtraction properties, length and width, and then find the length and width here. And then you're going to add the sum of both rectangles. So you're going to add the area of rectangles. And for the perimeter, all you're going to do is merely find out what these side lengths are. So you're going to add all of the lengths and the widths together of both rectangles combined, and you're going to add all side lengths. And that's specifically side lengths that are on the exterior, facing the exterior from the figure center. All right, let's move on to some practice problems. I'm going to be doing 3 practice problems, 1 for triangles, 1 for rectangles, and 1 for composite figures. So let's look at practice with triangles. These are going to be fairly simple, but my next video, I'm going to actually dive into really complex problems, and I'm going to break them down with you. But this is just a basic overview and preparation for our next video, next lesson. So this is area and perimeter practice. Find the area and perimeter of this figure. It's a triangle here, and this is a little bit of an overview of what you will be coming into and coming across with oblique triangles, which are triangles that aren't right triangles, any triangle that isn't a right triangle, and we're going to discover how this works. So as you can see here, this figure has a height of 4 inches and a length of 10 inches, and that's actually the entire length of this figure. Now, remember, we're just going to, since we figured out the height and the base, all we need to do is plug this into our equation, which is going to be, we're going to focus on area first. And all that's going to be is, it's going to be So I've just drawn in some measures here, 18 inches and 5 inches, to fill in this triangle so that we can actually calculate the area. So if we look at, we're going to first calculate to calculate the perimeter. So we're going to calculate the perimeter first. So perimeter, and we know that the perimeter is the sum of all sides. So we're just going to merely add all of the sides of this triangle. So that's 18 inches plus 5 inches plus 10 inches. And we get that our perimeter equals 18 plus 10 is 28. 28 plus 5 is 33. So our perimeter is 33 inches. And that's going to be 33 inches standalone, let alone. And then if we look at the area here, we can split this in half. Let's partition this out. I'm going to clear this out here real quick. Make a partition. So if I'm going to do area here, I'll write area here. The area of this figure will be base times height. Over 2, which equals 4 times 10, which is, since 4 is our height, indicated in the center, which equals 40, and we're going to divide 40 by 2 to get that the area is 20 units squared. So I'll write this out here. So area equals 20 units squared, and the perimeter equals 33 inches. Sorry, it's not 33 units squared, it's 33 inches. So that's a common mistake people make. They sometimes over-abuse the fact that we have to use units. Always keep it consistent with what unit you're given, because that would have actually been wrong if this were a test. Partially wrong, you would have been given partial credit since the unit is already indicated as inches. Now let's look at practice with rectangles. So we're going to figure out the area and perimeter of this rectangle. And we're going to relate it to a triangle with half of its area. So let's look at this rectangle first. So let's calculate the area here. Let's do perimeter first. So the perimeter equals the sum of all sides of a rectangle. So it's going to be 2 times the length or 2 times the width, or it can just be the sum of all sides, but let's use a shortcut. So it's going to be 2 times the length, and I'm going to label this side as the length and this side as the width. So it's going to be 2 times 4 plus 2 times 5. And if we simplify that, we get that 2 times 4 is 8, and 2 times 5 is 10. So that gives us a perimeter of 18 centimeters, and that's going to stay as centimeters solid. And then we're going to calculate the area here. So the area of a rectangle is length times width. So area equals length times width. So we know that our length is 4 and our width is 5. So we're going to multiply 4 by 5. We're not going to divide by 2 because this is a rectangle. And we get that we have 20 units squared. Sorry, 20 centimeters squared as our area. All right, so that problem's done. And now we're going to look at how this actually relates to a triangle. Like I said, for any right triangle, it's going to be the value of half of any rectangle that you're calculating for that same length and width. So half of this rectangle, I'm going to show you on a diagram here. I'm just going to try and sketch this out, etch this out, this little line here, partition. And if I'm splitting this in half, these two right triangles that I've just made on both sides here, this being right triangle number 1 and right triangle number 2, they both will have the same area, and they will both have a length and width of 4 and 5. And both of their areas will be half of this rectangle, which is basically half of the area of the whole rectangle, which is 10. Rewrite that. So it's going to be 10. 10 and 10. All right, let's move on to our final problem, practice with composite figures, and we're going to calculate area and perimeter. So we're going to find the area and perimeter of this composite figure. I'm just going to refer to the same diagram that we had before. So if we look at this figure here, we're going to try and calculate what its area and its perimeter of this figure are. But the first step that we need to do, first step in any composite figure problem, is we're going to actually split this figure apart into reasonable polygons that we can actually calculate through known area and perimeter formulas. Through known area formulas. For perimeter, we're going to just start off quickly with perimeter. We're going to add all of the side lengths here. So the perimeter equals addition of all side lengths. Is the sum of all side lengths, sorry. So we're going to take 5 feet here since we know that it's a side length. So I'm going to mark out what sides we need to actually find the perimeter for. So it's all exterior sides, so all sides that are on the outside of the figure and not on the inside. So this is one, this is another one, this here, this, and this. Those are all outward facing sides. So as you can see here, this first one is 5 feet as indicated by the problem itself. So it's going to be, I'm going to write this down here. I'm going to say sum of all sides. So I'm going to rewrite that real quick. So the sides here and perimeter equals perimeter equals 5, like I said before, 5, and then we have 6 here indicated for this side length, so it's going to be 6, and these are all in terms of feet, and then we have 2 down here, so that's going to be plus 2, and finally we have 3 out here. So we have 6, 2, and 3 that are indicated. So we have two of these missing side lengths here, and we can actually calculate that through relativity. So as we can see here, this long side length here is worth 5 feet here. So this one's worth 5 feet, and this one's worth 2 feet. So all we need to do is subtract them, 5 minus 2 feet. Since we have this length here and this length here, this length plus this length will add up to 5. So if you subtract 5 minus 2, we get that this is equivalent to 3 feet. We get that this is equivalent to 3 feet. I'll write this out here, 3. And then we're going to add that here. And then finally here, we see that 3 feet is going across here and 6 feet goes across the entire way. So that means the sum of this side here, 3 feet, plus this area here is going to equal 6 feet. So 6 minus 3 is 3. So this is also equal to 3. And that means you're going to also add 3 to that. So if we add these together, we get that 5 plus 6 is 11. 11 plus 2 is 13. 13 plus 3 threes is 13 plus 9, which equals 22. So our perimeter is 22 feet. Yes, okay. So let's look at area now. So the area for this figure, we're gonna split this figure up. I'm gonna do a partition that I think is fair here, but you can do it multiple ways. You can either do a partition down here, or you can do a partition here, meaning you'll have one shape, one long rectangle here and one small rectangle here, or you can make it 3 different segments. But I'm gonna make this 2 different segments because it makes the whole process much easier. But sometimes you're gonna have to split it up into much more segments, but try and keep it as short as possible by splitting it up into the least amount of sections as possible. So if we look here, we see that this bottom rectangle here, right here, I'm going to label this number 1, has a length of 5 and a width of 3. So we're going to multiply that. So I'm going to say 1, indicating our first rectangle equals 5 times 3. Equals 15. And then our second rectangle here has a length of 6 and a width of 2. So we're going to multiply that. So 2 equals 6 times 2, which equals 12. And we're just going to add these together to get that 15 plus 12 equals 27. And that's 27 units squared for our area. All right, guys, so that's it for today's lesson. Please make sure to subscribe down below, hit that like button on this video, and please make sure to hit that post notification bell because this has been at eCoreAcademy, at our eCoreAcademy YouTube channel. If you haven't already, please visit our website at www.ecoreacademy.org. We have full unlocked access to all of our note sheets, worksheets, and quizzes that go along with each and every one of our videos, organized into separate course studies, as well as other events and other bonus opportunities that are also given there, many perks and many tips and tricks. So all you need to do is make an account for free, and once you've signed up, you get access to everything there. Also, if you want to email us at eCoreAcademy@gmail.com, we have our full link down below in the description box. Please feel free to communicate with us if you have any questions or if you just feel like reaching out. Visit all of our socials at Facebook, Twitter, and Instagram. Check us a follow out there. We have the links down in the description box below as well. See what kind of content we have there and see if you want to share all of these videos through those mediums. Once again, guys, this has been AJ Raj. I hope you guys enjoyed this video. I will be making a predecessor extended problems for this video, for this lesson. So stay tuned for that, and I will see you guys in the next one. Peace.